Imagine you push a heavy book across your desk and feel its resistance. That's inertia, the tendency of an object to keep doing what it's doing unless you apply a force. But why does mass resist acceleration at all? Ernst Mach wondered, could an object's inertia actually arise from how it interacts with the rest of the universe's matter? This bold idea is known as Mach's principle. What exactly did Mach propose? Mach asked us to imagine a single rock floating alone in empty space. Would it even have inertia if there were no stars, galaxies, or planets around to push back? He suggested that inertia isn't an intrinsic property of mass, but emerges from the gravitational influence of all other masses in the cosmos. In other words, your book resists motion because every particle in the universe, from nearby desks to distant quasars, collectively defines what not moving means. How can we test such a cosmic claim? Question: if Mach's principle is true, would a rotating object feel different inertia if the distribution of distant matter changed? We can't rearrange galaxies at will, but we can look for clues in frame dragging, where a spinning mass drags space-time around with it. Experiments like Gravity Probe B measured how Earth's rotation twists local spacetime. While frame dragging confirms general relativity's predictions, it doesn't fully satisfy Mach's vision that inertia ties directly to the universe's mass distribution. Does Einstein's theory deliver on Mach? General relativity incorporates some Mach-like ideas, mass and energy shape spacetime, and spacetime tells masses how to move. But Einstein fell short of a truly Machian theory. You still have inertial frames even in empty solutions of his equations. Later extensions and alternative theories have tried to deepen Mach's link, but no consensus has emerged. Why does this puzzle matter? Because it forces us to ask, where do the rules of motion come from? If inertia is whispered to each object by the collective tug of the cosmos, then every push and pull on your coffee mug is, in a way, a dialogue with the farthest stars. Mach's principle remains an open question and a fascinating reminder that even everyday forces might be woven from the universe's grand tapestry. Mach's principle, named after physicist Ernst Mach, proposes that the inertia of any object, the resistance to acceleration, is not an inherent property but arises from its interaction with the mass distribution of the entire universe. This radical idea challenges Newtonian mechanics, where mass and inertia are intrinsic. Mach argued that if the stars and galaxies disappeared, a spinning bucket would not exhibit centrifugal effects, because there would be no reference matter to define motion. Inertia, then, is a relational property, not absolute, but caused by the gravitational influence of cosmic matter. Though not precisely formulated mathematically, this principle deeply influenced the development of modern physics. Einstein cited Mach's ideas as inspirational when developing general relativity, although the final theory does not fully implement them. It's like saying your resistance to being pushed depends not on your body alone, but on how every other person in the world is moving around you. Ewan's famous bucket experiment: water climbs the walls of a spinning bucket, showing centrifugal force. Proof, Newton said, of absolute rotation. Mach questioned this. What if the stars were rotating around a stationary bucket? Would the water still rise? If inertia is relational, then rotation and inertial forces depend on the relative motion between the bucket and the distant masses in the universe. This thought experiment laid the foundation for arguing that space is not an independent stage, but defined by the matter within it. The implication is that motion only makes sense relative to the entire universe. In a frame where the universe rotates around the bucket, Mach's logic suggests the same physical effect should occur: rising water. It's like spinning while blindfolded in a room. You only know you're turning if you can feel the walls around you. Einstein aimed to incorporate Mach's ideas into general relativity, GR, where space-time curvature is determined by mass energy. GR replaces absolute space with dynamic geometry influenced by matter, aligning somewhat with Mach's relational idea. However, solutions to Einstein's equations exist, like empty Minkowski or Gödel universes, that permit inertia and rotation without any matter present. This means general relativity allows but does not require Mach's principle to hold. GR is Machian compatible but not Machian obligated. A rotating frame in empty spacetime can still generate inertial effects like centrifugal force despite the absence of cosmic mass. It's like building a trampoline where the shape depends on who's standing on it, but also allowing it to have shape even when no one's there. According to Mach's principle, the inertia of a local object arises from gravitational interaction with all distant mass in the universe. This idea is hard to formalize because gravity propagates at finite speed and is extremely weak at cosmological distances. However, some theoretical attempts try to express inertia as an integral over gravitational potentials of all matter. These models suggest a cosmic background of gravitational drag that defines local inertial frames. Still, no consensus exists on whether such interactions are sufficient to explain inertia. Sayama's 1953 model proposed that inertial mass could emerge from gravitational induction due to the rest of the universe. It's like trying to define your identity not by who you are, but by your interaction with the entire crowd. The Machian worldview supports relationalism, the idea that motion, acceleration, and force are meaningful only in relation to other objects, not an absolute backdrop. Newtonian mechanics assumes absolute space and time, while Mach's principle implies that all motion is context-dependent. This philosophical divide shapes interpretations of both classical and modern physics. While general relativity leans relational, quantum field theory often assumes fixed background spacetime. Bridging these views remains an open conceptual and mathematical challenge. Barbault and Bertotti's shape dynamics formalism attempts to express gravity entirely in relational terms. It's like saying music has no meaning unless played in an orchestra. Each note is defined by its relation to the others. Inertia remains an emergent property in modern quantum theories as well. The Higgs mechanism, for instance, explains how particles acquire mass through interaction with the Higgs field, not directly with cosmic matter. But this does not fully address the origin of inertia as resistance to acceleration. Some cosmologists argue that if the universe's mass distribution changed, inertia might change too. Others propose that cosmic vacuum energy or dark matter fields may subtly influence inertial frames. In de Sitter or inflationary universes, the structure of spacetime alters the definition of inertial paths compared to a flat universe. It's like your body becomes harder to push, not because it's heavier, but because the whole room got denser. Testing Mach's principle is difficult because it involves hypothetical alterations to the entire universe. However, certain experiments, like frame dragging measurements by gravity probe B, show that massive rotating bodies can influence nearby spacetime and gyroscope axes. This lens-thirring effect is a partial realization of Machian thinking. Local inertial frames are affected by mass motion, yet this only confirms local interactions, not global Machian effects. No experiment has confirmed that removing distant mass changes local inertia. Frame dragging by Earth causes precession of gyroscopes in orbit, an effect predicted by general relativity. It's like spinning a spoon in honey. The surrounding fluid slightly twists, but you can't prove it's caused by the whole ocean. Mach's principle suggests that the universe's total mass energy distribution plays a role in defining the very structure of local physics. If true, this could link cosmology to fundamental constants, like the gravitational constant, G, possibly explaining its value through large-scale structure. Some theories, like Brand-Sticky's scalar-tensor gravity, attempt to make G vary depending on cosmic matter distribution. An attempt to Machianize G. This would make local physics explicitly dependent on the cosmos. However, such theories are tightly constrained by solar system and cosmological observations. The Brand-Sticky theory introduces a scalar field that mediates gravity and responds to the matter content of the universe. It's like the rules of chess, changing slightly depending on how many players are watching from the stands. Mach's principle remains an inspiring but unresolved idea. It elegantly links local physical behavior to the global structure of the cosmos, suggesting that being is inherently relational. While general relativity partially embodies it, a full Machian theory would likely require a deeper union of gravity, quantum mechanics, and cosmology. Whether inertia is truly universal or emergent from deep entanglements with all matter remains open. Mach's challenge continues. Redefine motion, mass, and reality through the lens of the universe itself. Modern cosmologists revisit Mach's principle in the context of holographic gravity, emergent space-time, and relational quantum theories. It's like asking whether your resistance to movement depends not just on your legs, but on how the stars remember your mass.